In this video, we're going to be looking at solving systems of inequalities. And so instead of the equal sign in our equations, we have inequality signs. When we're doing this, we want to graph these. When we're graphing these, if the inequality has the equal to part on it, we're going to graph it with a solid line when we're graphing. If it doesn't, if it's just strictly greater than or strictly less than, when we're graphing the graph, we're going to use a dotted line. When we're solving these systems to find out where they're intersecting, we're looking at it when these equations are equal to, instead of having the inequality signs there. Once we graph these equations, we want to determine which area to shave. Are we shaving above or below the graph that we graphed? And we can either determine by looking at it, or we can choose test points to see where to graph. So looking at that first equation, I would probably get y by itself before I graphed it. I noticed that in this equation, and I'm going to put the equal sign there, divide by x, or actually that's not. Let's look at y is greater than or equal to 4 over x. So I know that that looks like my graph y equals 1 over x. That 4 is just stretching it vertically. I can also see that I have a vertical asymptote at my x-axis and my y-axis, and I have a horizontal asymptote on my x-axis. So let's just plot some points. When x is 1, I know my y value is going to be 4. That's 4 over 1 is 4. When x is 2, 4 over 2 is 2. So I have a point at 2, 2 on this graph. When x is 4, my y value is 1. 4 divided by 4 is 1. So on the left of x equals 0, our graph looks like this. This is actually an odd function. This is symmetrical across the origin. F of negative x is equal to negative f of x. So I know I have this graph over here, symmetrical across the origin. If you didn't see that, you could plot some points. It's a solid line because I have the equal to part of my inequality. So guessing where I'm going to shade, I believe I'm going to shade inside in here, where I'm pointing my arrows towards. But let me test it. So let me choose a point that's not on my graph and see if it's a true or false statement. So let's choose one that's easy. How about let's choose one that is not in that area? And if I get back a false statement, then I chose the right places to shade. So let's choose where it's defined to. How about this point here when, well, x can't be 0. So that won't work. Can't have 0 in the denominator, right? How about 1, 1? So let's plug in 1, 1. Is that true or false? Is y, when y is 1, is that greater than or equal to 4 divided by 1? No, 1 is not bigger than 4. And so this 1, 1 is not in the correct region to shade. And so I did choose the right area. It's going to be shading here. And I'm just going to put my arrows, because I'm looking at places where both of my regions are shared, where they're both shaded in. So now let's look at y is greater than or equal to x squared plus 1. So we can use what we've learned about transformations of graph. So this looks like y equals x squared, but that plus 1 is shifting it up 1 unit. I know that coefficient in front of my x squared is positive, so I know my parabola is facing upwards. So I have a point at 0, 1. I can plug in a couple points if I wanted. When I plug in 1 for x, I have a y value of 2. This is symmetrical across the y-axis. If I plug in negative x for x, I get back the original function. It's an even function. So looking at this, I now want to determine where I'm shading. I believe it's inside the parabola. So I'm just going to put these arrows here, but I want to make sure that I'm choosing the right spot. So I can choose something that's inside that parabola or outside that parabola. So for instance, I'm going to choose one that's outside that parabola. How about below that parabola, 0, 0? If that's a false statement, then I chose the correct region to shade. So plugging in 0, 0 is 0 greater than or equal to 0 squared plus 1. Well, that's false. 0 is not greater than or equal to 0. So 0, 0 is not part of my solution set. And so now looking at where they're both shaded in common, notice it's this area up in here. So any point that falls in that area is going to be part of the solution to that system. Anything that's on these lines would also work. So there's our solution set. I may ask you to find where this is intersecting. And we can do that by looking at solving that system of nonlinear equations by doing so. Just because we're almost out of time, I'm not going to solve that there. I'm just going to go through more examples of solving well, it could be linear, but system of inequalities. So I have a system of linear inequalities in front of us. X is greater than or equal to 0. Y is greater than or equal to 0. So right there, that tells me I'm just looking at things in my first quadrant. Both X and Y have to be positive. I have 3x plus y is less than or equal to 6, and I have 2x plus y is less than or equal to 2. So if I was to graph this x is greater than or equal to 0, well, x equals 0 is that y-axis. And so x equals 0, again, is this y-axis. But I'm looking at things which are greater than or equal to 0. So it's solid line when I graph x equals 0. And it would be anything to the right of that line works for that inequality. For y is greater than or equal to 0, well, y equals 0 is my x-axis. Anything bigger than y equals 0 would be above the x-axis. So like I said, the region that they both share in common is just this first quadrant. So nothing that's outside of this first quadrant is going to be part of our solution set. If I want to look at the graph of 3x plus y is less than or equal to 6, well, let's put that in y equals mx plus b form. So let's subtract 3x. So I have y is less than or equal to negative 3x plus 6. So I can tell there that my y-intercept is at 6. I can tell that my slope here is negative 3, but I could write that as negative 3 over positive 1 or 3 over negative 1. So if I went down 3, if I went down 3, I'd go over 1 to the right. So I can see when x is 2, that's where I'm going to be crossing that x-axis. It has an equal to part to the inequality, so it's a solid line. And I need to know if I'm going to shade to the left or the right of that line. And so I believe that it's y is less than, so it's going to be to the left, but let's choose a point. I'm going to choose 0, 0. If I plug that in, the inequality is 0 plus 0 less than or equal to 6. Yeah, 0 is less than or equal to 6. So this point 0, 0 is part of my solution set. So I'm actually going to go to the left of this line. one more graph. And so let's graph 2x plus y is less than or equal to 2. If I subtract 2x on both sides, I would get y is less than or equal to negative 2x plus 2. So I can see my y-intercept here is 2. And I can see that my slope here is negative 2, but I can write that as negative 2 over positive 1 or 2 over negative 1. So if I go down 2, I'd be going over 1 to the, to the right. So if I go down another 2 over 1. So I get this line in here. This is values which are less than or equal to. So I believe that I'm going to be shading to the left of this. But we can test it by plugging in 0, 0 for x and y. So 0 plus 0 is less than or equal to 2 is correct. So the area that all 4 of those graphs which share in common would be this little triangle and down here. This would be part of this, all the points that fell inside here or were on those lines would be part of our solution set. So again, I'm going to want you to be able to find these points of intersection. In this case, I can see where they are. So like this corner right here is 0, 0. This point down in here, that was when x was 1, y was 0. This point up here was when x was 0, y was 2. So this was a quick introduction to systems of linear, or not linear, not necessarily linear, but systems of inequalities. I have more videos on that, so if you need to see some more examples, you can look at those.